Okay, 3.2, exponential decay. Learning about negative exponents, which we talked about a little bit yesterday already, but we'll do some more application of it today. The first term that you need is the term half-life. And half-life we talk about in terms of like a radioactive material because it will decay from what it is into something else, or population of a bacteria that dies off over time. So half-life is the length of time it takes for an unstable element to decay to 1/2 of its original amount. So let's say you start with 10 milligrams of something, and over time it decays, and eventually you only have 5 milligrams of it. The amount of time that takes is called its half-life. And then what's interesting is that the exact same amount of time will pass for it to decay to 2.5 milligrams. And then the exact same time will pass in order for it to decay to 1.25 milligrams. So half-life is the time it takes for half of an amount for an unstable element to decay to 1/2 of its original amount. So what is exponential decay? Exponential decay. We can use the concept of half-life to describe exponential decay. Half-life is really just a type of exponential decay. Half-life is exponential decay where the repeated factor is 1/2. You lose half, you lose half, you lose half. You multiply something by 1/2, then you have half of it left. You multiply it by 1/2 again, you have half of it left. That's just a factor that gets repeatedly multiplied, which will cause exponential decay. But you could multiply by a factor of 1/3, that would cause exponential decay. You could multiply by a factor of 4/5, that would cause exponential decay. Basically any factor that is in between 0 and 1.
So it's the same idea as like exponential growth in the sense that it's just multiplying itself again.
Exact same idea because it's still exponents, which is repeated multiplication. So let's get a definition down for exponential decay. This is a pattern of decay in which each term is multiplied, a pattern of decay in which each term is multiplied by a constant fraction between 0 and 1. And just like yesterday, we talked about the graph. Exponential decay will produce a graph that is decreasing at a constantly decreasing rate. What does that mean? Let me draw it out for you. Hopefully you have a little bit of space. You can draw this as well. Essentially, exponential decay says you're going to start with a certain amount, and it's going to decay. And it's going to get closer and closer and closer to 0. It's never actually going to reach 0. But the distance between the curve and 0 is going to get cut by the same fraction over and over and over and over and over again. And so you can see this is constantly decreasing, right? If we drew a tangent, it's decreasing, still decreasing, still decreasing, as in the slope is still negative. But it's decreasing at a constantly decreasing rate. So it's not decreasing as quickly as you move to the right as you move along in time, it's not decreasing as quickly. It's decreasing the most quickly right at the beginning. Okay, so you start with an amount, it decreases really quickly, and then it keeps on decreasing by the same fraction, but that ends up resulting in a decreasing rate of decrease. Lots of things to think about there. But that's what it looks like. That's the general definition of it. And same as yesterday with exponential growth, we talked about the finite differences. And we just want to make a note then, the ratio of successive finite differences is constant. And we'll see that as we move along. But basically yesterday we ended up with a situation where we had something like y values of 1, 3, 9, 27, and we realized that 3 over 1 was the same as 9 over 3, was the same as 27 over 9. The ratio of successive finite differences was constant. In that case, it was a number greater than 1. In this case, it's 3. Today, we're going to be looking at things that would be like this. And if you take successive y values or successive first differences, you'd end up with 8 over 16, which is 1/2, or 4 over 8, which is 1/2, or 2 over 4, which is 1/2, or 1 over 2, which is 1/2. That ratio of successive finite differences is going to be constant. Okay, taking that concept into the investigation, it says on page 7 in your notebook, uranium is commonly used as fuel for nuclear reactors. Uranium has several different forms or isotopes, some of which occur naturally and some of which are produced through a process called nuclear fission. One isotope, uranium-239 or U-239, has a half-life of about 2 years. So U-239, just jotting down some important information, has a half-life of 2 years. What does that mean? It means if you had a sample of U-239 and you just left it alone, in 2 years, you'd have half the amount of U-239, and the rest of it would have decayed into a different element. So that's what it says there, into a new substance. Suppose you have 1,000 milligrams. We're starting with 1,000 milligrams of U-239. How can we model the amount remaining over time? So check out your chart, and there's something interesting about it, is that the column with time doesn't count by ones. Why not?
Because it's over 2 years that it decays by half.
Yeah, because we're more interested in the number of half-life periods, the number of HLPs. Okay, so go ahead and fill in that column. And then our last column is the amount of U-239 remaining. And if we're starting with 1,000 milligrams, what's going to happen after one half-life period?
500.
What's going to happen after another half-life period? You sure you don't lose the other 500? It's half?
No, you have 500.
You have 500, you lose half of that. Go ahead and fill in the rest. Okay, is this table of values, does it demonstrate a linear trend, a quadratic trend, or an exponential trend?
Exponential.
It's an exponential trend. Why? Because we're doing an exponential decay lesson. How do you know?
Because if you were to take 500 and divide 1,000, you would get half. And yeah.
That's enough? That's enough proof?
If they all equal half.
Yeah, they all have to.
Well, yeah, that's
They're all divisible by 2.
Nope, they're not, and that doesn't matter. Okay? They have to create the exact same ratio. They all, if I take this over that, and then this over that, and this over that, and this over that, they all have to reduce to 1/2. They do, so it's exponential decay. Okay, so example 1, we're still talking about uranium-239, and we're learning that when it does decay, it forms a different material called plutonium-239. This is highly toxic waste material, and it has a much longer half-life period than uranium-239 does. The half-life period for plutonium-239, Pu-239, is 24 years. So we want to find out approximately how long it will take for 50 milligrams of plutonium-239 to decay to 10% of its original value. So a couple of things that are happening there. I'm going to say we're working with plutonium-239. This stuff is already written for you, but maybe you can underline it in the question. We have a half-life of 24 years. And we're going to start with 50 milligrams. So we have an original amount, A naught, is going to be 50 milligrams. And we want to find out how much is left. We want our final amount, 10% of original amount. Okay, there's my notes. Yours are probably just underlines in your problem. So the first thing we need to do is actually find out, we need to write an equation. So we need an equation for an exponential decay situation. And then we need to find out what amount we're actually going for, because 10% isn't an amount, okay? 10% is a ratio, but we're starting with 50 milligrams, so we're going to find out what 10% of 50 milligrams is. Before we do that, we need a equation to talk about this. So we're talking about the amount with respect to the number of half-life periods, okay? So this is going to be the new amount, the amount that's remaining. It's going to be equal to our original amount times our decay factor, which when you're talking about half-life is always going to be half, to the power of n. That means that we're going to half this amount. We're going to cut it in half n times. We're going to multiply it by 1/2 for as many half-life periods as we need to. I'm going to just quickly make a note of what all these pieces are, because you are going to need to memorize this. It's actually the exact same function as the growth function, except this number right here is the decay factor, because it's between 0 and 1. Decay factor. If this were exponential growth, it would be greater than 1. It would be called a growth factor. This over here is normally just called the amount. For the sake of helping us out, I'm going to call it the amount remaining, so that you know it's not the amount that you're starting with. And this is called A naught, which is initial amount. That's the amount that you're starting with. And the last thing that we need here is our number of years? No, number of half-life periods. So if I'm talking about a period of 24 years, what number should go here for n? 1. 48 years, n is 2. Okay, can you have in between those? Yeah, of course, it's still decaying. So you could have 36 years would be 1.5 half-life periods. Okay, so now we have our initial exponential decay formula, and all we need to do is fill that in with information that we know. We said the one thing that we wanted to know still before we start is what is 10%. So we know we're going to start with 50 milligrams. That's A naught, so I could sub that in. But I want to find out, I'm not trying to find out how much of something is remaining. I'm trying to find out how many half-life periods it's going to take to get a specified amount. The specified amount is 10% of 50. So since 10% of 50 is, and by the way, I'll write algebraically 10% of means multiplication. So 10% is 0.1 as a decimal times 50. Basically means take 50 and divide it by 10. It's 5 milligrams. So our amount remaining that we're aiming for is 5. The amount that we're starting with is 50. We're talking about half-life periods, and we do not know the number of half-life periods. And now our goal is to solve for n. Now, you're going to be a little bit disappointed because we can't solve directly for n because it's in the exponent. We don't have the skills to do that until much later in this course / next course. Okay, first step for isolating n, which, like I said, we can't do fully. But we can see that it's 50 times this group. Okay, so as we're stripping things away from n, we can still divide both sides by 50. Be really careful that you don't accidentally divide both sides by 5. That won't work. You need to divide both sides by 50. So if I look at my right side, if I divide by 50, it leaves me with 1/2 to the power of n. On the left side, 5 divided by 50 is 0.1. So now my only option is to get my calculator out and essentially guess. Okay, I'm going to guess a value for n. I'm basically saying I'm going to take 1/2 and I'm going to multiply it by itself n times in order to get 0.1. So what I want to do is just make a quick little table of values. That's going to be my guess and check. And maybe we'll see what happens if we put in, well, what number do you think? How many times are we going to have to multiply 1/2 by itself to shrink down to 0.1? 1/2 is 0.5, by the way.
Like 6.
Okay, go for it. Type 0.5 to the power of 6. What do you get?
0.015625.
No. 0.0, sorry, what? 0.01 something?
But you said no. What does that mean?
I recant. What? Give me your number.
I recant.
0.015625.
All right, is that pretty close?
Well, it's 0.2.
Wait, 6 times.
Well, careful. Look, 0.01. You need
Oh.
0.1, so you're actually 10 times too small right now.
So you did
So
So
I'd like to get
let's pick another number.
3.
3?
I have a question.
Let's try, yeah, sure,
Are you
let's try 3.
dividing these numbers?
0.125.
Ooh, if you do 0.5 to the power of 3, you get 0.125. That's pretty close.
Yeah, but not
It's still, and now it's a bit too big. So
4.
let's, wait, is it?
2. No, that's the closest.
So this value is a little bit too big. So we need to, in order to shrink it a bit more, we actually have to have an exponent that's bigger than 3. So I try like 3.3.
0.1.
Yeah, that's pretty close. Okay, that's a reasonable approximation. I'm going to just write a couple notes as we're thinking through this. So when we tried to the power of 6, our number was too small. So what that should tell us is that we need fewer half-life periods. Okay? Then when we put n as 3, 0.5 to the power of 3, our number was a little bit too big. Our value was too great. So we actually need more time. And then we tried 3.3 half-life periods, and this is a good approximation. Okay, the question says, how long will it take? What have we answered so far?
how many half-life periods.
We've answered how many half-life periods. So what do we need to do to our half-life periods?
Multiply it by 2.
Take your 3.3 half-life periods, multiply it by the actual half-life period, and you should get 79.2. What does that tell us?
It will take years. 79 years.
Yeah, it will take approximately 79.2 years to what?
For the 50 milligram sample of plutonium.
Nice. For a 50 milligram sample of plutonium-239 to decay to 10% of its original amount. Trivia question. What if you started with 1,000 milligrams instead of 50 milligrams, and you wanted 1,000 milligrams to decay to 10% of its value? How long would that take? Would it be different?
Yeah, I don't think that was right.
The trivia, it's the same. It would be exactly the same. No matter what you start with, no matter how much you start with, if you want to end up with 10% of that, it will take 79.2 years approximately. Okay, because it's a consistent ratio. Doesn't matter where you start with, you're going to cut it in half and then in half and then in half. So you'll get down to 10% because 10% is just a proportion of the original amount anyway. So 10% of 1,000 is more than 10% of 50. Does that make sense?
But it'll take the
Okay, example 2, 3, and 4 are just working with exponents and particularly negative exponents. We also have some fractional bases coming up in the last example. But all this is a review of how to use your laws for exponents when they involve negative exponents. So again, what do you do if you have a base to a negative power? All you have to do is take the reciprocal to a positive power. Okay? So you make the exponent positive and you take its reciprocal. So 3 to the power of negative 2 is the exact same as 1 over 3 to the power of 2. We can reduce that. 1 over 3 to the power of 2 is 1 over 9. Okay?
oh
This works in any case at all. If you have, here's the law, if you have a base, right, to a negative exponent, that is 1 over that base to its positive exponent. Notice the value, the number didn't change, just the sign changed. We could write this a different way. You could write it like this. What if you have 1 over b to the power of negative n? Well, the reciprocal of this with a positive exponent is just b to the power of n. Okay, both of these statements are the exact same rule. Let's look at the second one. The second one, we have 6 to the power of negative 2 times 6 to the power of 3. We notice right away that we have a product. Okay, so it's a power law, but it's a product law of powers. So powers means, do you understand what I'm saying when I say powers? This whole statement is a power. 6 to the power of 3, that's a power. It has a base and an exponent. Okay, so this is now the product of two powers, a power here and a power here. What do you notice about those two powers?
they were the same.
They have the same base. They have the same base. So if they have the same base, you can apply the product law, which says keep the base and add the exponents. Okay? Keep the base, add the exponents. This is the power law, sorry, the product law, right? Product law of powers. And I can write it quick. It says if you have a base times any x to the power of any exponent and you're multiplying it by a power with the same base but the exponent might be different, all you have to do is add the exponents. It doesn't matter if they're positive or negative. You take them and you add them. So we had negative 2 plus 3, which reduced down to 6. C. C says negative 2 in brackets to the power of negative 4 plus 4 to the power of negative 2. So we have a couple things happening here. We have the reciprocal is going to happen, this first law that we talked about, a negative exponent law. And all that does, allows us to rewrite this situation. So here the base is -2 and the power is -4. So we have 1 over -2 to the power of +4. Our second term was 4 to the power of -2. That's now going to be 1 over 4 to the power of 2. We can work with these still independently. -2 to the power of 4, that's just 4 factors of 2 multiplied by each other. So you get 2 times 2 is 4, times 2 is 8, times 2 is 16. And because it's an even exponent, I know there's an even number of negative factors, which is going to result in a positive product. Okay, a positive answer. It's -2 times -2, that's positive. Times another negative, that would be negative. Times another negative, that would be positive. So since there's 4, I know this is going to be positive. And 2 to the power of 4 is 16. 4 to the power of 2 is also 16. So now we have 1/16 plus 1/16. How many 16ths?
2.
Is that my final answer?
No, 1/8.
1/8. And I'll just do D beside it here. If you have space, you can keep working down, your choice. D says we're going to take 4 to the power of -2. This time the exponent is in a bracket with the 4, and that whole thing is raised to the power of -3. Then we're going to divide it by 4 to the power of 8. Now right away I see something that they've done. Two things, one of which we already described. We have a power to another power. So this is a power of powers law. And then they did something nice. They gave us the same base on both of these expressions. So here we go. Power of power laws says that if you have a power raised to an exponent, you multiply the exponents. Okay, so this piece I can reduce and rewrite like this. The exponent becomes -2 times -3. And I can leave my second part as divided by 4 to the power of 8. Well, -2 times -3 is +6. That is called the power of powers rule. And jot that down. This is power of powers. And now I have the quotient rule because I have the same base in both of these powers and there's division in between them. So it's the opposite really of our product law over here where we added the exponents. Now we're going to subtract the exponents. 6 minus 8. Please do not accidentally put 8 minus 6 just because 8 is bigger and you like doing that. That would be wrong. Okay, it's 4 to the power of 6 over 4 to the power of 8, which is 4 to the power of -2. Are we done?
No.
No, I want to express using, I want to evaluate. So I actually want to just get a value. What do I have to do to this thing?
So the
One
fraction.
over 4.
1 over 4 squared, which is 1 over 16. Okay, the other thing that we did right here, from here to here, is the quotient law.
What if it wasn't the same base?
If it was not the same base, you would not be able to do this. But let's say they expressed this instead of being, 4 to the power of 8, they expressed it as like 2 to the power of something. You can actually make this look like it's to the power a base of 2 because 2 is the square root of 4. Anyway, there are ways to mix and match and make it work, but you don't have those skills yet. We might get there. Okay, example 3, we are, again, just simplifying expressions. We're going to use the exact same laws in the exact same way, but you'll notice this time we don't just have numbers, we have variables. Okay, so remember, x is a number. We just don't know what it is. This x is the same as this x is the same as this x. They're all involved in powers, so we have the same base. That's good to know. And what's happening to each power?
Multiplication.
They're being multiplied. Okay, so we're looking at a product law for powers. What does the product law say? It says that you can keep the base and add the exponents. Okay? Now, I wrote a plus sign in here because the rule is to add the exponents, but plus -3 is just the same as -3. Okay? So what we're looking at here is -2 minus 3, that's -5, plus 4, that brings us up to -1. And one of the points of this exercise is to only use positive exponents. So I'm not done. We also need to use our negative exponent law. Sorry, that's now positive, which exponent x to the power of 1 is just x. Okay? So what did we use? What law did we use here?
The negative exponent law.
Product law here. And then I don't even know the name of this thing. It's just how you deal with negative exponents. All right. All right, in B, we have a situation where we have factors in the numerator and factors in the denominator. So we have a division sign here, which means I'm going to be working with the quotient rule. There are different ways of doing this one. I could take the reciprocal of this and put it in the numerator, and take the reciprocal of this and put it in the denominator. Then I'd be working with all positive exponents right at the bat. But what else I can do is just relate my common bases, and I can say, okay, I have a power with a base A being divided by a power with a base A. So I can just think about my A's, and I have 2 minus -1 as the exponent, because the exponent in the numerator is 2, being divided by A with an exponent of -1. So I just have to take my base of A and go 2 minus -1. Okay, and that's being multiplied by factors of B. How many factors of B? Well, we have -3 minus 2. Okay, that's the quotient rule happening twice. Quotient rule. What does that reduce to? Well, 2 minus -1, that's 2 plus 1, that's a to the power of 3, times b to the power of -5. But I'm only allowed to use positive exponents. So what happens to this factor of b to the power of -5? Goes in the denominator.
So you can put the A in the denominator. And that's okay.
Numerator.
A
That's what I
stays
meant.
in the numerator
That's what I meant.
because it ends up with a positive exponent. B goes to the denominator because he has a negative exponent. So somewhere in here is this. I skipped this step. Okay, it's kind of like this. 1 over b to the power of 5, and then we went to there. This b I could have done a different way. I could have applied the negative exponent rule first and taken the reciprocal of the a exponent here and the b with a negative exponent here, and then it would look like this. I would have a squared in the numerator. He's positive, so he'll just stay. But this guy would get flipped to the numerator with a positive exponent. And my factors of b, this b to the power of 2, he's already in the denominator with a positive exponent, so that's fine. But this one, I'd have to take the reciprocal and change the sign. So now he gets bumped from the numerator to the denominator. And then you can see how this reduces right away to 3 factors of A over 5 factors of B. Okay? This way might even be easier to do rather than apply the quotient rule. 2 ways to do the same thing. Okay, this last one is a little bit more complicated. You really need to pay attention to the exponents and not lose any of your little numbers. Now, this -3 is on the outside of the brackets. That means it applies to everything inside the brackets. It's going to affect this part, and this part. Okay? There's 2 different ways you could do this. You could right away take the whole thing, don't do this. You could rewrite it in the denominator with a positive exponent and then work through using the power of powers law. I'm not going to do that right away because I want to focus on the power of powers law. What does that mean? That means that this to the power of negative 3 is again going to apply to each piece, each factor inside our bracket. So we have 2 to the power of negative 3 times u to the power of 3, which is what we're starting with here, this factor, 3 factors of u, to the power of negative 3. Well, if you remember our power of powers rule, that means I can multiply my exponents. And then the last 2 factors of v to the power of negative 2 also gets multiplied by an exponent of negative 3. Now we can see how this reduces and bumps certain things into the denominator if needed, okay? So, starting with this one, 2 to the power of negative 3, that's going to be 1 over 2 to the power of 3. U to the power of 3 times negative 3, that's going to be u to the power of negative 9. Notice right now, if I write it this way, that this term, this factor, is still in the numerator, okay? So I could even put like a little multiplication there and a little multiplication here. I don't need to do that, but it helps you to see that they're separate factors right now, but they're really all essentially one statement. It's still one term because it's all multiplication. And then factors of v are negative 2 times negative 3, that's positive 6. So you can think about this a couple of different ways. I already have a fraction set up, and I know I'm going to have terms in the numerator, pieces I should say, they're not individual terms, pieces in the numerator, and this piece is going to get moved to the denominator, right? So I draw my fraction line. In the numerator, I have 1 and 6 factors of v. So in the numerator, all I really have is v to the power of 6 times 1. Anything times 1 is just itself, so the only thing I need to write is v to the power of 6. In the denominator, I already bumped my 2 to the power of negative 3. What's 2 to the power of 3? 8. I can evaluate that, right? So I don't know what u is, I don't know what v is, but I do know what 2 to the power of 3 is. That's 8. And I have 9 factors of u in the denominator. So this is simplified. And before we move on, maybe I'll just make a note here that we applied the power of powers rule. Okay, quick run through. If you have the same base and they're all exponents being multiplied by each other, then you can just add the exponents with that base. Okay, so if you see a default operation of multiplication in between each piece, each factor, just add the exponents. Done. Because we ended up with a negative exponent here, we flipped it into the denominator. Here we saw a division line. Okay, that meant that we were going to be using the quotient rule. The quotient rule says if you have the same base, you can just subtract the exponents. And because we're dealing with multiplication and division, you could focus just on the a's and just on the b's separately. Okay. Another way to make that clear is that I could have rewritten this whole thing like I did over here. Could have even rewritten it a different way. I could have put them all in the numerator. We could have had a to the power of 2, a to the power of 1, b to the power of negative 3, and b to the power of 2, all in the numerator. Okay? This statement, this statement, this statement are all the exact same. They all reduce to that using quotient rule and using the reciprocal of a negative exponent rule. The last one that we used was the power of powers rule, which means if you have a power to another power, you just multiply those exponents. And in this case, the exponent applied to 3 different pieces, and we had to be careful to apply 2 to the power of negative 3, this to the power of negative 3, and this to the power of negative 3 all together. Example 4 uses the exact same laws, but this time we have fractional bases. So the base is 1/3. Okay, and you're going to need to get good at this because, I mean, in exponential decay, the base is always going to be a fraction. So what happens here? Well, I can see that it's to the power of negative 1. So what do I need to do?
Flip it.
Reciprocal. Flip it.
3.
Okay, so the reciprocal of 1/3 is 3. So all I have then is 3 to the power of 1, which is 3. Okay? I could also do this a really awkward way if you want to see what is actually happening in between here. Basically what you have, according to the rule says if you have something to the negative exponent, you have to put that 1 over that. So according to that, we would actually write 1 over 1/3 to the power of 1. Okay? 1 over 1/3 is 3. Not going to explain that. I've done that before in a different video this year already. Okay, B. B is negative 27 over 8 in brackets to the power of negative 2. What are we doing here? Yeah, we're taking the reciprocal because we see we have a negative exponent. So what we're going to do is we're going to, instead of negative 27 over 8, we're going to have negative 8 over 27. And now it's to the power of positive 2. Now what do we need to remember? Well, this to the power of positive 2 applies to the 8 and to the 27. Okay? I could rewrite that off to the side. This is negative 8 over 27 times negative 8 over 27. Okay? Question. The negative sign. I left it out front. What does the negative sign apply to? The 8 or the 27? Or both? Girls, if I'm doing this, should I make the 8 negative or the 27 negative or both?
It
Watch.
just goes in front of it.
Yeah, I really just have to remember that this is this factor is negative and this factor is negative. If I did it to both,
That's positive.
I don't actually have a negative number anymore. So that is wrong. My preference is to do it to none of them and then just count my negative factors. Or what you could do is you could count it as negative 8 times negative 8, which is positive 64, over 27 squared, which is 729. And that is fully reduced. Okay. Another way to rewrite this, if you don't want to rewrite it like this is true, but this is also equal to negative 8 squared over 27 squared. Okay. This statement, this statement, this statement, this statement, and this statement are all the exact same. That's why we use equal signs. So the rule that's happening here is really an extension of the negative exponent rule, but it says that when your base is a fraction to the power of negative n, that's any negative exponent, you just flip your base. You flip your base, take the reciprocal of your base, and it's to the power of a positive value, the same number that's there, but you change the sign. Practice problems can be found on page 166. Numbers 1 through 8. Enjoy.